Well, hello and welcome to IB Biology Notes with me, Dr. Kimo. This is A1.1 Water. These are the contents of the current topic. Water is the medium for life as we know it. Life happens in water. Life is thought to have originated in water. Now, many substances, including minerals and biomolecules, can dissolve in water, and this allows them to move around and collide with each other, thus undergoing metabolic reactions. Most metabolic reactions still take place in water. For example, the cytoplasm is mostly water. This means that within your body, almost all the chemical reactions that happen in water. And metabolic reactions are the chemical processes which occur within living organisms and are necessary for life. So metabolic reactions, those are the chemical reactions of life. Water needs to be in a liquid state. So the temperature should be between approximately 0 and plus 100 degrees Celsius. The water molecule is polar. Oxygen and hydrogen atoms in the water molecule, they form covalent bonds. This means that they share electrons with each other. The illustration on the top shows this, how oxygen and hydrogen share electrons. In water and most other molecules, this sharing is not equal. Oxygen exerts a stronger pull on the shared negatively charged electrons than hydrogen does. And as a consequence, the molecule has a negative and a positive pole. It is said to be polar. And the colored illustration on the right shows how the oxygen side of the water molecule is more negatively charged than the hydrogen side of the water molecule. You see the minus and the plus signs. And this is because oxygen is pulling these shared electrons towards itself, and this leads to the oxygen side becoming more negative than the hydrogen side. You don't need to know about these numbers in biology. If you do chemistry, then you will learn more about them. They are called electronegativity values. Having said all this, the overall charge of the water molecule is neutral. Polarity enables hydrogen bonds. Hydrogen bonds are attractive intermolecular forces. Inter means that they form between molecules. They are very weak compared to covalent or ionic bonds, but they still have significant effects on the properties of water, such as cohesion, adhesion, its solvent properties, and its thermal properties. More about this later. Please look at the illustration on the right. The hydrogen bonds are always drawn as dotted lines, and the negative pole of one water molecule is always opposed to the positive pole of another water molecule. Cohesion. You've probably noticed that water molecules stick to each other. For example, look at the leaf in the background. This is called cohesion, and it makes water form droplets. It causes surface tension, which allows some insects to walk on water, like the one on the bottom right here. It is also a reason behind capillary action, which plants utilize to transport water and nutrients from the roots to the leaves. You can see an experiment below on the left where the water is climbing up along thin tubes. On the top right, you can see American astronaut Karen Newberg watching a sphere of water. It's a water droplet in the absence of gravity. Adhesion. Water molecules also stick to polar surfaces. This is called adhesion. Cohesion and adhesion act together, for example, to form water droplets on surfaces. On the image below, you can see how water molecules form hydrogen bonds with each other. That's the yellow dotted lines. That is cohesion. And with the underlying surface, that's the black dotted lines. That is adhesion. Also on the right, the spider web, there you see how water forms droplets, cohesion, and sticks to the web, adhesion. Adhesion is also important for capillary action. Water transport in plants, that's where capillary action comes in. In plants, water molecules stick to the xylem vessel walls, which helps prevent them from sliding back down. The water molecules also stick to each other, forming a water column. When water evaporates from the openings on the leaf, the water column is pulled upwards to replace the water that was lost. And in the illustration, you see how the water molecules stick to the walls and to each other. And remember, cohesion, water to water, adhesion, water to something else. And that something else needs to be polar. Water as a solvent. Water is an excellent solvent. Ions and polar molecules dissolve well in water, for example, sodium chloride and sucrose. Non-polar molecules do not dissolve well in water, for example, lipids, such as oils and fats. Water molecules form hydrogen bonds with solutes. In our example here on the right, the solute is a salt, like sodium chloride. The positive pole of the water molecules turns toward and forms hydrogen bonds with negatively charged ions or molecules, well, in this case, ions. So the negatively charged ion, which is green in this illustration and will correspond to chloride, forms hydrogen bonds with the positive pole of the water molecule. You can see the hydrogen side turning towards the green circle, which would be chloride. And vice versa, which means that the positive ion, in this case sodium, the yellow circle, forms hydrogen bonds with the negative side of the water molecules, which is the oxygen side. So the water molecules, they rip apart the lattice structure of a salt that is put into water until the ions have mixed with and dissolved in the water. The shell of water molecules around the ions prevent the ions from regrouping back into a lattice. If you have problems keeping track of all these sol words, have a look at the sentence at the bottom. A solute is a material that dissolves in a solvent, resulting in a solution. In this case, the solute would be sodium chloride and the solvent would be water. Metabolism. The solvent properties of water allows for a multitude of compounds and ions to dissolve in the watery substance that is the cytoplasm. This allows them to move and interact with each other and with enzymes which catalyze specific metabolic reactions with high precision. You know already, metabolism, it's the chemistry of life. Now, metabolism can be divided into catabolism, the breaking down of molecules, and anabolism, the synthesis of molecules. So, breaking or building. Water is often called a universal solvent, but non-polar molecules do not readily dissolve in water. You can see the picture of a glass with olive oil and water, and they form layers, they do not mix. Transport. Water is a transport medium in both plants and animals. In plants, so-called xylem and phloem vessels transport dissolved minerals and the products of photosynthesis. In animals, blood transports dissolved nutrients, waste, gases, and hormones. Blood also transports blood cells. The thermal properties of water. Water stays a liquid over a broad temperature range. The specific heat capacity of water is high, and liquid water is heavier than ice. This has consequences. Let's compare water and methane, because these properties of water are quite unusual. These two molecules have more or less the same mass. However, you can see the melting points and the boiling points are very different. Also, the range of liquid water is 100 degrees Celsius. For methane, it's only 22 degrees Celsius. The specific heat capacity is much higher for water than for methane, which means more energy is needed to heat up water than to heat up methane. For water, it's 4.22 joules per gram per degree Celsius. And the latent heat of vaporization is higher for water than for methane. More energy is needed to vaporize water, for water to go from liquid to gas, than for methane to do the same. Now, when things cool down, their density increase. And this is true for water. When liquid water cools, its density increases. But after plus 4 degrees Celsius, the density starts to decrease again, which means water becomes lighter. When water freezes, its density decreases by a further 9%, so it becomes even lighter, which means ice is lighter than water. As a consequence, ice floats on water, and this has huge consequences for life in water. Imagine this sheet of ice falling to the bottom. That would not be good for all the organisms living in the water. Buoyancy, that's another physical property of water. The density of living organisms is similar to that of water. Water provides an upward force which allows, for example, fish to move in all directions using only a modest amount of energy. In the water, organisms don't need to support their entire weight as they do on land. That's true for the fish, That's true for the plant on the left. Extraplanetary origin of water on Earth and reasons for its retention. Now we are moving into additional higher level territory. Water from space. Hot temperatures and volcanic activity on early Earth are thought to have expelled any water that would have been present at the time. Instead, Earth's water is thought to have arrived in the form of icy asteroids about 4 billion years ago, during a period called the Late Heavy Bombardment. These asteroids had kept their water because they formed further away from the Sun, where it was much colder. According to one model popular among astronomers, the asteroids were thrown off their paths towards the inner rocky planets, that's Mercury, Venus, Earth, and Mars, due to outward orbital migration of the gas giants, that's Jupiter, Saturn, Uranus, and Neptune. Outward orbital migration means that these gas giants moved away from the Sun, so their orbits moved away from the Sun. And as they moved with their huge gravity, they threw some of the asteroids off their paths, so some of them in the end crashed into Earth, bringing a lot of water with them. Water is retained on Earth due to Earth's gravity and temperature. Due to cohesion, water is retained more easily in liquid form than in gas form. And the higher the temperature, the higher the velocity of molecules, and the easier it is for them to escape. However, the upper atmosphere, from where water vapor could potentially escape, is too cold to allow water molecules to reach escape velocities. Also, water tends to condense into clouds at much lower altitudes, so water doesn't really tend to reach the upper atmosphere. Life in space. Life as we know it requires water. It's difficult to imagine any kind of life without water. Astronomers are therefore looking for water as an indication of the possible presence of life. Planets that orbit other stars than the Sun are called exoplanets. And exoplanets in the habitable zone, or the Goldilocks zone of their host star, are of particular interest. A habitable zone means that it's not too hot, not too cold for liquid water to exist. These are the planets that astronomers focus on when they are trying to find hints of life around other stars. The James Webb Space Telescope is used for many things. One of them is looking for water on distant exoplanets. Exoplanets being planets that orbit stars other than the Sun. This figure shows that there just might be water in the atmosphere of the hot gas giant exoplanet WASP 96b. And astronomers can tell this with the help of spectroscopy, where they analyze the light that reaches us from distant objects. Closer to Earth, on Mars, water is thought to have once flown in, for example, the Osuga Valley on the Martian surface, which really looks like a river delta. Also, cross-bedding in rock formations on Mars show evidence of movement of water. And sedimentary rock formation in itself also typically requires water. that's all for now. See you next time.